For a century, we rode pillars of fire into the sky. Chemical flame carried us to orbit, to the moon, to the edge of possibility. But fire is only the beginning. Cut to archival imagery of Saturn V launches, roaring plumes, shockwaves tearing across launch pads. Then the frame fractures into holographic overlays, equations, plasma simulations, reactor cores, magnetic field lines twisting like cosmic serpents. The next era of propulsion will not burn. It will bend, accelerate, ionize, split, and perhaps one day, fuse the stars. Inside a vast orbital shipyard circling Earth, autonomous drones assemble the deep space vessel AURORA. Unlike rockets of the past, AURORA carries no towering chemical stages. Its spine is long and skeletal, lined with radiators that unfold like metallic wings. Engineers float in zero-G, guiding robotic arms that install the heart of the ship, a next-generation Hall-effect plasma array inspired by systems flown on missions like Psyche. Blue plasma erupts in a silent test burst, contained within magnetic fields. Electric propulsion, the narrator continues, trades brute force for patience. Instead of explosive thrust, it whispers, but it whispers for months, for years, until a spacecraft reaches velocities chemical rockets can never touch. Graphics show ions accelerated through electromagnetic grids, specific impulse numbers climbing far beyond conventional engines. The exhaust glows cobalt, steady, elegant, efficient. Cut to a research facility in Texas where the descendants of the Vasimer concept, variable specific impulse magnetoplasma rocket, hum within superconducting coils. Plasma, heated to millions of degrees, spirals inside magnetic nozzles without ever touching solid walls. Scientists monitor temperature curves and magnetic containment maps. Vasimer, says a lead physicist, her voice layered over the cinematic score, lets us shift gears in space. High thrust to leave orbit. High efficiency to cross the void. The engine fires during a lunar transfer test, a luminous violet beam extending kilometers behind a robotic tug. The moon grows closer, not over days, but in a fraction of the traditional transit time. Transition to darker tones. A sealed chamber opens to reveal a compact nuclear thermal propulsion core, a collaboration between NASA and DARPA under programs like Draco. The reactor's uranium fuel elements are engineered to withstand searing hydrogen flow. Nuclear thermal propulsion doubles the efficiency of chemical rockets, the narrator explains. Liquid hydrogen surges through reactor channels, superheated, expelled at immense velocity. A simulation shows a crewed Mars transfer ship cutting travel time significantly, reducing radiation exposure and mission risk. The camera lingers on the reactor's glow, controlled Starfire, domesticated for exploration. But the future does not stop at fission. In a high-security laboratory, experimental fusion confinement chambers pulse with magnetic arcs. The direct fusion drive concept flickers to life in holographic projection, a compact fusion system that could power both propulsion and onboard systems for deep space missions. Fusion, whispers the narrator, the same force that lights the sun. If harnessed, it could take humanity to the outer planets in years instead of decades. A visualization shows a spacecraft accelerating continuously, flipping mid-journey, decelerating into orbit around Saturn. Rings shimmer in reflected plasma light. Back in orbit, AURORA receives another upgrade. Laser sail modules folded into its cargo bay. On Earth's surface, a phased array laser complex powers up, inspired by directed energy propulsion research, such as deep ion. Gigawatts of coherent light converge upward. In simulation, a lightweight probe unfurls a reflective sail. The beam strikes. The craft accelerates without propellant, riding pure photons. Propellantless propulsion, the narrator says, turns light itself into momentum. The probe streaks outward, a silver speck racing beyond Pluto's orbit in record time. The score swells. AURORA is complete. Electroplasma arrays for efficiency. nuclear thermal boosters for departure, fusion research modules for future retrofits, laser sail deployment bays for interstellar precursors. It is not one technology, but a convergence, a bridge between what exists and what is becoming. Engineers gather at observation windows as the ship slowly rotates, sunlight glinting across its radiators. Every generation redefines distance, the narrator concludes. Sailors crossed oceans. Aviators cross continents. Rocket pioneers cross gravity. Now we prepare to cross the solar system, not in leaps of flame, but in sustained acceleration. Mission control counts down, not from 10, but from 100, symbolizing a century of rocketry. At 0, the nuclear thermal stage ignites, not with a thunderous explosion, but a contained, blinding plume. AURORA begins its outward spiral from Earth orbit. As it clears safe distance, the plasma engines engage, dozens of blue spears extending into darkness. The ship does not lurch. It glides, constantly accelerating, building speed minute by minute. Earth shrinks behind it, luminous and fragile. The camera pulls back further still, beyond the moon, beyond cislunar space, revealing trajectories plotted toward Mars, the asteroid belt, Jupiter's moons. Lines of light trace possible futures. This, the narrator says softly, is ignition not of engines, but of an era. Fade to black. Darkness gives way to a lattice of stars. AURORA is now weeks in her outward spiral. Blue plasma plumes burning steadily behind her like twin rivers of light. There's no roar in space, only momentum, quiet, relentless, exponential. The narrator returns, softer now, more intimate. In the age of fire, thrust was an explosion. In the age of plasma, thrust is persistence. Inside the propulsion ring, charged xenon atoms are stripped of electrons, ionized into a glowing storm. Magnetic fields channel them through acceleration grids, hurling them aft at velocities exceeding 50 kilometers per second. Each ion imparts only a whisper of force, but together, over months, they build unimaginable speed. Graphics overlay the scene. Specific impulse curves dwarfing chemical engines, efficiency ratios climbing past 3,000 seconds. Engineers monitor the Hall effect thruster arrays, their golden discharge channels glowing electric blue. The design descends from systems proven in deep space, but scaled, clustered into megawatt-class arrays powered by vast solar sails and auxiliary reactors. Cut to Earth orbit, a constellation of cargo tugs, smaller siblings of AURORA, ferry supplies between Earth, lunar orbit, and Mars staging depots. They rely entirely on electric propulsion. Gone are the violent launch windows and razor-thin fuel margins of the past. Instead, trajectories arc gracefully through space like calligraphy. A flight dynamics officer traces one such path in augmented reality. Continuous thrust, she explains, changes mission architecture. We don't coast and correct. We accelerate, adjust, adapt all the way. Cargo that once required multiple chemical launches now rides efficient plasma ferries, reducing cost and expanding reach. The infrastructure of a multi-planet civilization is quietly forming. Inside AURORA, Captain Alara Moreau floats beside a panoramic viewport as Mars grows from a red star into a textured world. She watches engine telemetry scroll across her wrist display. Thrust steady. Reactor auxiliary at nominal output. The ship's solar arrays shimmer. Ultralight perovskite films spanning hundreds of meters, converting sunlight into megawatts. Yet as distance from the sun increases, another power source stirs. In the aft module, a compact nuclear electric propulsion system hums, a fission reactor driving high-power ion thrusters. Unlike nuclear thermal propulsion's explosive heating of hydrogen, this reactor feeds electricity to plasma engines, combining endurance with efficiency. The narrator interjects. Nuclear electric propulsion extends electric propulsion beyond the warmth of the sun. Where solar fades, reactors endure. The camera dives into the reactor core. Control drums rotate minutely, balancing neutron flux. Heat pipes glow as they transfer energy to turbines and power conditioning units. Every watt is precious. Every gram of propellant accounted for. AURORA accelerates continuously, her velocity climbing into tens of kilometers per second relative to Earth. The mathematics of constant acceleration reshapes the mission timeline. Arrival at Mars will take weeks less than conventional Hohmann transfers. Radiation exposure drops. Psychological strain lessens. The ship is not drifting. It is journeying with intent. On Mars orbite, à construction plateforme away. Robotic arms assemble fuel depots stocked with green monopropellants, safer alternatives to hydrazine developed by emerging aerospace companies. These non-toxic propellants power landers and orbital maneuvering systems, reducing risk to crews and infrastructure. The narrator frames it as evolution. The future of propulsion is not only faster, it is cleaner, safer, sustainable. Shots of technicians in Martian orbit handling propellant modules without bulky hazmat suits contrast sharply with archival images of toxic fuel protocols from the 20th century. Back aboard AURORA, a briefing unfolds in the mission hub. A hologram of the variable specific impulse magneto-plasma rocket rotates above the table. Though still experimental, a prototype module is mounted on the ship's spine. Chief Engineer Arun Kessler gestures to the display. Vazimir gives us flexibility. We can dial thrust up to maneuver in Martian orbit, then switch to high-efficiency cruise mode for the asteroid belt. Plasma temperatures reach millions of degrees, contained entirely by magnetic fields shaped by superconducting coils cooled near absolute zero. The contrast is poetic. Star-hot plasma guided by materials colder than interstellar space. A test ignition begins. Magnetic fields bloom like invisible petals. Argon plasma spirals and accelerates through a magnetic nozzle, forming a brilliant violet exhaust that stretches into the void. The thrust is stronger than the Hall arrays, yet still efficient. Telemetry spikes, then stabilizes. Applause ripples through the crew cabin. We are witnessing the bridge, AURORA says quietly, between near-future and far-future propulsion. Montage. Cargo vessels using pulsed plasma thrusters leapfrog between lunar gateways. Autonomous probes equipped with magneto-plasmodynamic engines depart for Jupiter, their exhaust luminous and fierce. A research craft tests advanced superconductors that allow higher current densities, pushing plasma propulsion toward even greater power levels. Each technology is incremental alone, revolutionary together. As AURORA approaches Mars, she performs a continuous thrust deceleration burn, flipping orientation and firing engines forward, bleeding velocity smoothly instead of relying on abrupt capture maneuvers. The red planet fills the viewport. Olympus Mons casts a colossal shadow across the dawn. Phobos drifts nearby like a captured relic. The narrator's voice carries quiet triumph. With plasma, we do not arrive by chance or gravity alone. We arrive by design. Docking clamps engage with the Martian orbital platform. Engines power down to a gentle glow. Yet AURORA's journey is only beginning. Beyond Mars lies the asteroid belt, rich in metals and volatiles. And beyond that, Jupiter's icy moons, where subsurface oceans wait. To reach them efficiently, propulsion must evolve once more. Plasma and fission are steps. The next leap will demand something bolder, something closer to the power of stars. The camera drifts outward, framing Mars, AURORA, and the faint blue glimmer of her plasma engines cooling in orbit. Patience, the narrator concludes, is the hidden force of the cosmos. Gravity shapes worlds over eons. Plasma engines shape destinies over months. And humanity, at last, is learning to harness both. Fade into the deep crimson of Martian dusk, where new engine modules await installation. Experimental, nuclear, perhaps even fusion-bound. Mars hangs beneath AURORA like a rusted jewel, its thin atmosphere glowing along the Terminator line. Docked to the orbital construction ring, the vessel undergoes her most ambitious upgrade yet. The narrator's voice lowers, deliberate. Electropropulsion gave us patience. Nuclear propulsion will give us reach. Inside a reinforced bay shielded by boron carbide panels and water jackets, engineers prepare the nuclear thermal propulsion module, a reactor designed not merely as an experiment, but as a workhorse for interplanetary acceleration. Its lineage traces back to 20th century concepts, revived and refined under programs such as Draco, but this iteration is denser, safer, smarter. The reactor core is revealed in slow rotation. Hexagonal fuel elements composed of high-assay low-enriched uranium embedded in ceramic metal composites capable of withstanding temperatures beyond 2,700 Kelvin. Liquid hydrogen tanks line the spine of AURORA like translucent arteries. The narrator explains, unlike chemical rockets that rely on combustion, nuclear thermal engines heat propellant directly using fission. No flamme, no oxygen, just pure thermodynamic expansion. Countdown begins within the Martian orbital exclusion zone. Crew secure themselves as hydrogen floods through the reactor channels. Control drums rotate outward. Neutron flux rises. The reactor achieves criticality in a smooth, controlled climb. Hydrogen superheats instantly, expanding and rushing through the nozzle at extraordinary velocity. The exhaust plume erupts brilliant white against the darkness. Not explosive, but immense, sustained. The thrust dwarfs the plasma engines. AURORA trembles for the first time since leaving Earth. Specific impulse nearly double that of chemical propulsion, announces engineer Kessler over comms. Thrust to weight within mission tolerance. The numbers cascade across the HUD, 900 seconds and climbing. The ship departs Mars orbit in a decisive burn, carving a trajectory toward the asteroid belt. Unlike the quiet whisper of plasma, nuclear thermal propulsion is a statement, a declaration of power harnessed and contained. Montage. Archival footage of early nuclear propulsion tests dissolves into present-day engineering marvels. Radiation-hardened AI monitoring neutron flow. Autonomous shutdown systems prepare to scram the reactor in milliseconds. The narrator contextualizes the risk and reward. Fission carries responsibility. Shielding mass must be balanced against performance. Heat must be rejected through vast radiators. But the payoff is transformative. Weeks saved on journeys measured in millions of kilometers. AURORA's radiators unfold like silver wings, glowing faintly as they dissipate waste heat into space. The reactor cycles between high-thrust burns and standby modes, conserving fuel. The crew feels the sustained acceleration, artificial gravity generated not by rotation, but by thrust itself. For hours at a time, decks tilt subtly under their feet. It is a return to sensation long absent in microgravity voyages. Beyond Mars, the sun shrinks. Solar intensity drops. Plasma engines shift to reactor-supplied electricity, while the nuclear thermal stage prepares for another burn. Ahead lies Ceres, largest body in the asteroid belt, a waypoint for refueling and research. The narrator's tone becomes visionary. With nuclear propulsion, the belt is no longer distant frontier. It becomes crossroads, cut to a mining platform anchored to a metallic asteroid. Autonomous drills extract water ice and volatiles, electrolyzing them into hydrogen and oxygen. Hydrogen reserves replenish AURORA's tanks. A closed-loop economy emerges, resources harvested in space to propel deeper exploration. In-situ resource utilization, AURORA remarks during a briefing, turns destinations into fuel stations. Yet even as fission proves its worth, whispers of a greater ambition echo through the ship's research wing. Behind reinforced magnetic shielding lies a prototype fusion confinement system, not yet operational for full thrust, but nearing readiness. The direct fusion drive concept forms its blueprint. Magnetic fields compressing plasma to initiate fusion reactions that produce both charged particles for propulsion and abundant electrical power. Unlike fission, fusion promises minimal long-lived radioactive waste and exponentially greater energy density. Scientists observe plasma instabilities dancing across containment fields. Superconducting magnets, cooled with cryogenic precision, struggle to maintain equilibrium. Fusion is not brute force, says lead physicist Dr. Ishan Rao. It is balance, pressure against pressure, magnetism against chaos. Simulation projections display travel times to Jupiter reduced dramatically. Continuous acceleration, enabling flip-and-burn trajectories previously impossible within practical mass limits. AURORA departs Ceres with a combined propulsion strategy. Nuclear thermal for departure surges, nuclear electric for steady cruise, plasma arrays fine-tuning trajectory. This orchestration of systems marks a turning point. No longer reliant on a single engine paradigm, humanity has entered the age of hybrid propulsion architecture. Each method complements the others, optimized for phase, distance, and mission profile. As the vessel accelerates toward the outer planets, Jupiter's gravity well looms in predictive overlays. Radiation belts swirl like invisible storms. To reach its icy moons, Europa, Ganymede, Callisto. Propulsion must be precise and powerful. A miscalculation could mean entrapment or catastrophic exposure. The crew gathers in observation as the reactor spools for a major burn. The narrator's voice deepens, resonant. Controlled Starfire. The splitting of atoms not for destruction, but for expansion. For centuries, humanity feared the power within the nucleus. Now, that power becomes our engine. Ignition. The plume blossoms once more, brighter against the dimmer sun. Acceleration presses gently, but persistently. The stars shift position ever so slightly as velocity compounds. Days later, Jupiter dominates the frame. A colossal sphere of swirling storms and lightning flashes visible even from orbit. AURORA's engines throttle precisely, shaping a capture trajectory toward Ganymede. As the ship settles into Jovian orbit, reactor output tapers to standby. Plasma arrays glow faintly, maintaining station. The camera pulls back to reveal the immensity of Jupiter and the tiny brilliance of AURORA beside it. Fission carried us here, the narrator concludes. But to go farther, to Saturn, to Neptune, to the Kuiper frontier, we must ignite something greater. Not the fire of atoms split, but the fire of atoms joined. The fusion chamber hums in the background, magnetic coils charging for the first sustained reaction test. Jupiter's immense gravity curves space like a living presence. Lightning fractures its clouds in continent-sized flashes, illuminating AURORA as she orbits Ganymede in preparation for the next great experiment. The narrator's voice carries both reverence and anticipation. Fission split the atom. Fusion seeks to unite it, to replicate the engine of stars within a chamber forged by human hands. Deep within the ship's reinforced core module, the prototype fusion drive awakens. Its architecture draws from decades of magnetic confinement research and the evolving vision of compact systems, such as the direct fusion drive, a propulsion concept promising both thrust and abundant electrical power. The chamber is ringed by high-temperature superconducting magnets, cooled to near absolute zero. Within their invisible cage, plasma will burn hotter than the sun's core. Dr. Ishan Rao stands before the control array, eyes reflecting holographic magnetic field models. Initiating plasma injection. Deuterium and helium, 3 rare, precious isotopes harvested from lunar regolith and gas giant atmospheres, stream into the confinement chamber. A pulse of energy ignites the mixture. Instantly, plasma erupts into a radiant sphere contained only by magnetic tension. It writhes, unstable, luminous beyond comprehension. Temperature climbing past 100 million Kelvin, an engineer reports. Field stability within acceptable deviation. The narrator continues, measured and awed. Fusion differs from fission not only in scale, but in elegance. Instead of splitting heavy atoms, it merges light ones, releasing immense energy in charged particles. Those particles can be directed, shaped by magnetism into thrust. Magnetic nozzles engage. A fraction of the fusion plasma is guided aft, expelled in a controlled stream of high-energy particles. Unlike the white blaze of nuclear thermal propulsion or the blue whisper of ion engines, this exhaust burns brilliant white gold, tinged with ultraviolet arcs invisible to the human eye. Sensors translate the radiation into visible light, revealing a spear of contained starfire stretching into space. Acceleration begins, subtle at first, then unmistakable. Not explosive, but continuous and powerful. The readouts climb beyond anything previously achieved. Specific impulse exceeds 10,000 seconds. Reactor mass-to-thrust ratios stabilize within projected margins. For the first time, fusion propulsion transitions from theory to sustained operation. Outside, Jupiter's massive form recedes as AURORA begins a trajectory towards Saturn. The journey that once required years will now take months. The ship performs a calculated burn, then enters sustained acceleration, building velocity day after day. Crew experience artificial gravity generated by thrust, walking along decks angled slightly toward the stern. It feels natural, grounding, almost terrestrial. The fusion reactor's secondary output floods the ship with electrical power. Laboratories hum with energy abundance. Shielding systems strengthen against cosmic radiation. Laser communication arrays beam high-bandwidth data streams back to Earth. Fusion does more than propel, AURORA reflects. It empowers. Montage. Saturn's rings shimmer in distant sunlight. Titan's hazy atmosphere glows amber. Enceladus vents plumes of icy vapor into blackness. AURORA threads through the ring plane, fusion exhaust reflecting in crystalline arcs. Autonomous probes detach, each equipped with miniaturized plasma engines derived from the ship's primary systems. They descend toward icy moons, scanning for biosignatures within subsurface oceans. The narrator's voice expands beyond the immediate mission. With fusion, the outer planets are no longer remote outposts. They become neighbors. Scientific expeditions become routine. Infrastructure follows discovery. On Titan's orbit, a construction node assembles fuel skimmers designed to harvest helium-3 from the atmosphere. Robotic collectors dive through orange clouds, extracting trace isotopes for future fusion drives. Resource cycles begin to close. Humanity is no longer dependent solely on earthbound materials. The solar system transforms into an interconnected network of energy and propulsion. Yet fusion remains delicate. Plasma instabilities ripple across the magnetic containment fields. During one tense sequence, fluctuations threaten quench conditions in the superconducting coils. Alarms pulse crimson. Engineers adjust field harmonics in real time, damping oscillations before containment falters. The ship shudders as thrust momentarily drops. Stability regained, reports Dr. Rao, breath steady but eyes sharp. Fusion is not conquered. It is negotiated. The narrator underscores the truth. Engineering a star is not about domination. It is about balance, sustaining forces that naturally seek chaos. AURORA resumes full thrust. Saturn diminishes behind her as the trajectory extends toward the ice giants, Uranus and Neptune, realms never before visited by crewed missions. Continuous acceleration, followed by mid-course inversion, allows deceleration upon approach, compressing decade-long journeys into a fraction of the time once imagined. Inside the ship, crew gather at the observation dome as Neptune's deep cobalt hue fills the horizon months later. Supersonic winds ripple across its atmosphere. Triton orbits nearby, geysers casting faint plumes into darkness. Fusion exhaust reflects faintly in the planet's blue glow, a symbol of human presence in distant territory. From chemical flame to electric whisper, from fission's split to fusion's union, the narrator concludes, voice resonant across the stars. Propulsion has evolved with our courage. each engine a mirror of our ambition, each breakthrough a step farther from the cradle. The camera drifts beyond Neptune, into the Kuiper belt where icy worlds drift in frozen silence. AURORA's fusion drive continues to burn, its light a manufactured star against the void. But even fusion may not be the final chapter. Ahead lies deeper darkness, distances so vast that even sustained Starfire feels small. In the ship's forward laboratory, a new experiment awaits activation. A compact antimatter containment ring, still dormant, shimmering with potential. The narrator whispers one final line as the screen fades toward interstellar night. To cross the gulf between stars, we may need to harness matter's shadow. Beyond Neptune, sunlight thins to a distant spark. The Kuiper belt stretches like a frozen halo around the solar system, scattered with ancient remnants of planetary formation. AURORA moves through this twilight frontier under steady fusion thrust, her engineered star blazing against the cosmic dark. The narrator's voice returns, hushed and anticipatory. Fusion reshaped the outer planets. But to cross the abyss between stars, propulsion must transcend propellant itself. Inside the forward research module, shielded by layered magnetic confinement rings and redundant failsafes, a device no larger than a grand piano hums softly. Within its electromagnetic traps rests humanity's most volatile achievement, a few nanograms of antimatter. Suspended in vacuum by precisely tuned magnetic fields, the particles never touch the chamber walls. Antimatter, the narrator explains, is matter's mirror. When they meet, both vanish, releasing energy at nearly total mass-to-energy conversion. The most powerful reaction known to physics. Dr. Rouse studies the containment readouts. We are not building a bomb, he reminds the crew during briefing. We are building a catalyst. The concept is measured, deliberate, antimatter-initiated fusion. Instead of relying solely on extreme magnetic compression, microscopic bursts of antimatter trigger fusion reactions with greater efficiency, lowering containment thresholds and increasing thrust density. It is controlled annihilation, orchestrated at atomic scales. A test begins. A fraction of a nanogram is released into a fusion microchamber where deuterium pellets await. Magnetic lenses guide the antimatter into contact. For a fraction of a second, annihilation occurs. Gamma flashes ripple outward but are captured by dense shielding. The resulting energy spike ignites a fusion pulse far more intense than previous cycles. Exhaust erupts brilliant white-blue, sharper and more focused. Acceleration increases measurably. Pulse efficiency up 12%, reports engineering. Containment stable. The narrator frames the moment. Antimatter is not a primary fuel. Its production remains costly and rare. But as a trigger, it transforms fusion into something fiercer, more compact. A bridge between stellar fire and interstellar ambition. Outside, the Kuiper belt objects streak past as velocity climbs to unprecedented levels. Continuous acceleration pushes AURORA toward fractions of a percent of light speed. At these velocities, even dusk grains pose danger. The ship deploys a forward plasma shield, a projected magnetic field that ionizes and deflects incoming particles. The bow of the vessel glows faintly as micrometeoroids vaporize before impact. Yet another propulsion experiment awaits deployment, one that carries no onboard fuel at all. In the inner solar system, a colossal phased array laser installation tracks AURORA's trajectory. Built upon concepts pioneered by directed energy research programs such as DeepIN, the array combines thousands of synchronized beams into a coherent column of light spanning millions of kilometers. Laser link confirmed. Mission control transmits across the vast distance. AURORA deploys a reflective sail from her dorsal spine. Not a fragile sheet, but a metamaterial lattice engineered at the nanoscale to withstand intense photon pressure. The sail unfurls like a silver continent, shimmering against the stars. When the laser array fires, A spear of invisible energy strikes the sail, transferring momentum without mass. The ship surges forward, fusion and antimatter pulses synchronized with photon pressure. For the first time, propulsion is multimodal across energy domains: nuclear, particle, and pure light acting in concert. The narrator's tone swells with wonder. Propellant once defined the limits of travel. Now, momentum can be beamed across space. Energy can be transmitted without tanks or exhaust. Weeks pass. The sun diminishes to a bright star behind them. The heliosphere's boundary approaches, a vast region where solar wind yields to interstellar medium. Instruments detect fluctuations in charged particles, the subtle boundary of our star's influence. The crew gathers silently as AURORA prepares to cross. Fusion drive at sustained burn. Antimatter catalyst cycling in controlled microbursts. Laser sail retracting as beam intensity fades with distance. Velocity climbs higher still. "We are approaching heliopause," AURORA announces. Her voice carries weight beyond procedure. The narrator speaks softly, reverently. For all of human history, every voyage unfolded beneath the sun's domain. To cross beyond is to step outside the cradle entirely. The boundary arrives not as a wall, but as a shift, a change in particle density, a whisper in magnetic readings. AURORA passes through, engines blazing. The solar system becomes a shrinking sphere behind them. Ahead lies interstellar night, dotted with distant suns. Inside the propulsion module, antimatter containment rings shimmer faintly. Engineers discuss future scaling. Larger traps, improved production methods, perhaps one day harnessed from high-energy particle accelerators orbiting Mercury or harvesting naturally occurring antimatter within planetary magnetospheres. For now, they proceed cautiously. The power is immense. Precision is survival. A final test in this phase begins. A sustained antimatter-assisted fusion burn lasting hours instead of minutes. Magnetic field strain, behold. Exhaust luminosity intensifies, casting long shadows across the ship's hull. Acceleration presses crew gently into their harnesses. Velocity approaching 1% light speed, reports navigation. A silence follows, all mingled with disbelief. At this rate, journeys to the nearest stars compress from tens of thousands of years to mere centuries, still vast, but within conceptual reach for generational vessels or cryogenic explorers. The narrator concludes this chapter with quiet gravity. We have learned to split atoms, to merge them, to harness annihilation and ride photons. Each method a testament to our refusal to remain confined. Yet the stars remain distant. To truly voyage among them, propulsion must bend not only matter and energy, but space itself. The camera pans outward, revealing AURORA as a luminous arrow streaking through interstellar medium, a man-made star departing its birthplace. In the ship's theoretical physics lab, holograms swirl, equations describing space-time curvature, exotic matter distributions, and a concept once relegated to speculation, the warp metric. The narrator whispers as darkness deepens. If velocity cannot be increased without limit, perhaps the fabric of space can. Interstellar space is not empty. It breathes with faint hydrogen atoms, ghostly magnetic fields, and the relic radiation of the Big Bang. AURORA streaks forward under sustained antimatter-assisted fusion thrust, a manufactured star carving a luminous path through darkness. Yet even at 1% of light speed, the nearest stellar neighbor remains decades away. The narrator's voice returns, contemplative. There comes a threshold where propulsion by force alone becomes insufficient. When pushing harder yields diminishing returns. Beyond that threshold lies a radical thought. Do not move faster through space, move space itself. Inside the theoretical propulsion laboratory, holographic equations arc through the air, solutions to Einstein's field equations, energy density tensors, curvature maps. The Alcubierre metric rotates slowly in projection, a bubble of contracted spacetime ahead and expanded spacetime behind. A warp drive does not break relativity, Dr. Rao explains during a briefing. It respects the local speed limit. The ship itself remains stationary within a bubble. It is space-time that travels. The concept remains experimental, bordering on speculative, but decades of quantum field research have transformed impossibility into hypothesis. Early calculations once demanded exotic negative energy equivalent to entire stars. Modern refinements suggest drastically reduced requirements, still immense, but perhaps achievable with controlled quantum vacuum manipulation. Casimir cavities line the laboratory walls. Parallel superconducting plates position nanometers apart to generate measurable negative energy densities through vacuum fluctuations. Tiny but real. Step 1 is not faster than light travel, AURORA says calmly. Step 1 is measurable curvature. AURORA reduces fusion thrust to standby. Antimatter containment remains active but idle. The ship's power grid diverts nearly all output to the experimental spacetime field generator, a toroidal ring encircling the vessel's midsection. Superconducting coils surge with current, generating a magnetic field intense enough to distort instrumentation. Quantum vacuum modulators activate, amplifying Casimir effects within layered metamaterials engineered at atomic precision. Field harmonics synchronized, reports engineering. Energy density within projected tolerances. Outside the ship, nothing appears different. Stars remain fixed, darkness unchanged. But internal sensors detect minute anomalies. Picometer shifts in laser interferometers, infinitesimal deviations in local spacetime geometry. The narrator's tone grows reverent. For the first time in history, humanity measures curvature not from a planet or a star, but from its own creation. The field intensifies gradually. A faint shimmer surrounds AURORA, visible only through specialized instruments translating gravitational gradients into color. Blue hues gather at the bow, red trailing at the stern, compression and expansion. The warp bubble is embryonic, fragile, smaller than projected. Stability at 0.0000003 metric distortion, Dr. Rao announces. It is microscopic, yet monumental. Energy consumption climbs steeply. Fusion reactors ramp back to full output, antimatter catalysts pulsing in microbursts to supplement demand. The ship becomes a symphony of advanced propulsion. Technologies working in unison, nuclear fire powering quantum geometry. Then something shifts. External star fields distort subtly. Light from a distant red dwarf bends fractionally around the ship's perimeter. Not lensing from gravity wells of massive bodies, but from AURORA herself. The crew watches in stunned silence. We are not accelerating, AURORA whispers. But our reference frame is moving. Navigation confirms it. Relative displacement occurs without corresponding inertial forces. No thrust presses against the crew. No acceleration registers on onboard sensors. Yet external coordinates change faster than fusion propulsion alone could account for. The bubble is weak, partial, unstable, but real. The narrator contextualizes the triumph. Warp is not about speed in the conventional sense. It is about topology, about shortening the distance between 2 points by reshaping the medium that separates them. Alarms flicker. Energy gradients spike along the port side of the toroidal ring. A containment fluctuation threatens asymmetry. If the bubble collapses unevenly, tidal forces could ripple dangerously across the hull. Engineers dampen the oscillation, redistributing power flow and recalibrating vacuum modulators. The shimmer stabilizes. For 12 seconds, AURORA sustains measurable space-time distortion beyond laboratory scale. 12 seconds that redefine propulsion forever. Then the field dissipates, coils cooling rapidly, quantum plates returning to baseline separation. Silence fills the command deck. No explosión, no catastrophe. Only a data stream, unlike any recorded before. We bent space, Dr. Rao says softly. Not enough to reach a star, but enough to prove the principle. The narrator's voice carries quiet triumph. Chemical rockets conquered gravity. Plasma mastered efficiency. Nuclear fire extended reach. Antimatter intensified fusion. And now, humanity has touched the geometry of a universe itself. Outside, the interstellar medium drifts past. AURORA resumes fusion acceleration. Yet something fundamental has changed. Distance is no longer an absolute barrier. It is a variable awaiting engineering refinement. In the lab, simulations project future iterations. Larger field rings, higher negative energy densities, stabilized warp metrics requiring a fraction of previous power estimates. Theoretical travel times to Alpha Centauri compress from decades to months, then weeks in cascading models. The obstacles remain immense. Energy production, quantum stability, space-time feedback effects. But the boundary has shifted from fantasy to frontier. AURORA addresses the crew in a ship-wide transmission. Today we did not outrun light. We did not break physics. We respected it and learned how to speak its deeper language. This is how every era of propulsion begins. A fragile first spark. The camera pulls back, revealing AURORA once more under fusion thrust, her experimental ring faintly glowing as it cools. The nearest stars shine ahead, no longer unreachable myths, but coordinates awaiting refinement. The narrator concludes in measured cadence. To bend space is to acknowledge that motion is not the only path forward. The universe is not merely traveled, it is shaped. Fade to distant starlight, equations still echoing in holographic afterimage. The stars ahead no longer feel impossibly distant. After the first measurable warp distortion, AURORA travels with renewed purpose, fusion engines steady, antimatter catalyst silent but ready. Yet within the propulsion laboratories, debate intensifies. Warp curvature demands extraordinary energy. Antimatter remains rare. Fusion, though powerful, still requires reaction mass. The narrator's voice enters thoughtfully. Every propulsion system before this one has obeyed the same principle. Expel something and move in the opposite direction. But what if thrust could arise without exhaust? Inside the research bay, a cylindrical apparatus rotates slowly within magnetic. Suspension. It resembles neither rocket nor reactor. Instead, it houses ultra-high Q resonant cavities, superconducting chambers designed to trap electromagnetic waves at immense intensities. The concept, once controversial and debated across decades, has evolved into something far more rigorous: field momentum propulsion. Dr. Rao addresses the crew. Conservation of momentum is not negotiable. But momentum can exist in fields: electromagnetic, quantum vacuum, gravitational. If momentum exchange occurs with space-time itself, thrust may emerge without conventional propellant. The device powers up. Microwave energy floods the asymmetric cavity, bouncing billions of times per second between precisely contoured walls. Sensors measure nanonewton-level forces, barely perceptible but consistent. Unlike earlier speculative devices, this system incorporates quantum vacuum plasma coupling layers, engineered metamaterials that interact with zero-point fluctuations. The narrator explains, measured and careful. In deep vacuum, space is not empty. Virtual particles flicker in and out of existence. If engineered fields can bias those fluctuations, even minutely, reactionless thrust might not violate physics, but redistribute momentum across the vacuum itself. Test sequence begins. Fusion reactors divert a small fraction of power to the resonant drive. The chamber hums, its interior glowing faintly as electromagnetic intensity rises. Precision laser interferometers track displacement relative to inertial reference masses isolated from the hull. At first, nothing. Then a drift. Tiny. Persistent. Microacceleration confirmed. Engineering reports. Magnitude low, but non-zero. No propellant flow detected. Silence grips the deck. Unlike fusion or antimatter, this propulsion produces no visible exhaust. No plume. No radiation spike. AURORA simply begins to gain additional velocity beyond fusion baseline. The force is small compared to nuclear drives, yet it is continuous and requires no reaction mass. In the vacuum of interstellar space, continuous microthrust compounds dramatically over months and years. The narrator contextualizes its potential. A drive without exhaust would free spacecraft from propellant mass constraints. Missions could last decades, centuries, limited only by power generation. Power remains the key. The resonant field drive demands stable megawatt input. Fusion supplies it, while antimatter-assisted pulses recharge superconducting capacitors that buffer energy surges. The propulsion architecture grows increasingly symbiotic. Nuclear fire feeding field momentum, which in turn supplements warp field experiments. Navigation confirms cumulative effects. Over days, the exhaustless drive contributes measurable delta V. The increase is modest but undeniable. More importantly, no violation of conservation laws is detected. Minute photon leakage from the cavity correlates with momentum transfer, suggesting interaction with external fields rather than isolated thrust generation. Dr. Rao smiles faintly. We are not defying physics. We are negotiating with it. Outside, interstellar dust density rises slightly as AURORA approaches a sparse molecular cloud. The plasma shield glows faintly, deflecting particles. Fusion thrust tapers while the field drive continues uninterrupted, silent, and invisible. Meanwhile, warp research progresses. The toroidal ring undergoes structural reinforcement using carbon nanotube lattices grown in microgravity. Quantum vacuum modulators are recalibrated using data from the field momentum experiments. A hypothesis emerges. Combining sustained microthrust from the exhaustless drive with low-level warp curvature may reduce total energy demands. Instead of forcing large distortions, the ship could surf subtle gradients in space-time. A test of this synergy begins. Fusion reactors stabilize at cruise output. The resonant field drive sustains microacceleration. The warp ring activates at minimal distortion amplitude, far below previous thresholds. Instead of a pronounced bubble, a gentle curvature gradient forms ahead of the vessel. External starfields shift slightly more than expected from thrust alone. Energy consumption remains manageable. For the first time, propulsion is not singular but layered. Fusion providing baseline acceleration, antimatter boosting when necessary, field resonance supplying continuous exhaustless thrust, warp curvature reducing effective path length. The narrator's tone carries quiet revelation. Perhaps the future of propulsion is not one grand invention, but orchestration. A symphony of forces, nuclear, quantum, photonic, geometric, working together. Weeks pass. Velocity increases beyond earlier projections. Communication latency with Earth grows significant. Messages take hours, then days. The Sun is now one star among many. On the observation deck, AURORA records a log. We once believed propulsion was about power alone. Bigger rockets, stronger explosions. Now we see it is about efficiency of interaction with matter, with energy, with space itself. She watches as a faint aurora-like glow dances across the warp ring's edge, the signature of low-level curvature stabilized by field momentum thrust. Suddenly, sensors detect a gravitational anomaly ahead. A rogue planet drifting between stars, its mass bending light from distant suns. AURORA adjusts course using the exhaustless drive with exquisite precision, conserving fusion fuel. The ship glides past the dark world, mapping its atmosphere and magnetosphere. Even in deep interstellar space, propulsion becomes a tool not only for travel, but for exploration and maneuvering in uncharted gravitational landscapes. The narrator concludes this chapter with contemplative gravity. An engine without exhaust challenges centuries of intuition. Yet progress has always followed the same arc, from fire to plasma, from atom to vacuum. The universe is not resistant to movement. It simply requires understanding. As Aurora continues outward, data from all propulsion systems converge into a unified model, a blueprint for vessels yet to be built. The crew senses they're no longer merely testing engines. They're defining the physics of a civilization destined for the stars. Fade to a distant binary star system shimmering faintly ahead, their first true interstellar destination. The warp ring pulses gently, the resonant drive humming invisibly. The narrator whispers one final thought. If thrust without exhaust is possible, what else in the vacuum awaits discovery? The binary system ahead grows from twin pinpoints into distinct suns, one amber, one pale white, locked in gravitational embrace. Aurora approaches not as a wanderer, but as an emissary of engineered propulsion. Fusion burns steady. Field momentum drive humming invisibly. Warp ring sustaining a low, efficient curvature gradient that subtly shortens the path before them. The narrator's voice carries restrained wonder. For the first time, humanity arrives at another star not by drifting for generations, but within a single lifetime. Velocity bleeds off in a long, graceful inversion maneuver. Aurora rotates, fusion exhaust flaring forward in a sustained deceleration burn. Artificial gravity shifts direction across the decks as thrust presses from bow to stern. Antimatter-assisted pulses spike briefly, compressing the deceleration window. The warp ring modulates curvature to minimize transit time while preserving structural tolerances. The stars loom large now. A faint halo of exoplanets emerges in sensor overlays, gas giants, rocky bodies, a super-Earth within the habitable zone of the amber primary. Light curves confirm atmospheric signatures. The crew stands silent before the panoramic dome as alien sunlight reflects across Aurora's hull. Target planet designation, EOS, navigation announces. The narrator deepens in tone. Propulsion is not only about departure. It is about arrival, about breaking across light years with the same precision used to leave home. Aurora deploys a new propulsion subsystem for the first time in full-scale operation. A magnetic sail, or mag sail, a vast superconducting loop extending hundreds of kilometers via ultralight conductive filaments. Powered by fusion-generated current, the loop creates an immense magnetic field bubble ahead of the ship. As they plunge into the stellar wind of the binary system, charged particles collide with the magnetic field, transferring momentum and slowing the vessel without expending propellant. The effect is gradual but profound. Velocity drops steadily as the stellar wind presses against the magnetic shield. Plasma streams ripple visibly along field lines, forming aurora-like arcs stretching across kilometers of space. Deceleration efficiency above projections, engineering reports. Minimal fusion expenditure. The narrator contextualizes the elegance. By interacting with a star's own outflow, the ship transforms solar wind into brake force. No exhaust, no fuel, only magnetism and motion. As speed decreases further, the magsail retracts in coordinated segments, filaments spooling inward like threads of light. Aurora transitions to fusion and field momentum propulsion for fine orbital insertion around EOS. The planet fills the viewport, oceans glinting copper beneath alien clouds, continents shadowed in hues unfamiliar yet beautiful. Spectrometers detect water vapor, oxygen traces, complex carbon compounds. A moment of silence envelopes the command deck. "We crossed interstellar space," AURORA says quietly, "and we arrived with fuel to spare." But propulsion innovation does not rest at arrival. To explore this system sustainably, energy infrastructure must precede colonization. Autonomous drones deploy toward the inner system to begin constructing a beamed energy array around the white dwarf companion. Its stable luminosity ideal for phased laser installations. Inspired by early directed energy propulsion concepts, these arrays will eventually beam power across interplanetary distances, enabling light sail cargo ships to traverse the system without carrying propellant. Meanwhile, AURORA tests gravitational assists within the binary dynamics. By threading between the two stars at calculated intervals, the ship gains orbital energy boosts while minimizing fusion burn. The narrator explains, gravity is propulsion's silent partner. Properly harnessed, it lends momentum freely, a dance choreographed with celestial bodies. On Eos orbit, lander craft attach, powered by compact green monopropellant thrusters derived from earlier Martian systems. Their descent is controlled, efficient, non-toxic. Surface beacons activate, relaying atmospheric data upward. Back aboard AURORA, the propulsion lab analyzes long-duration performance metrics. Fusion reactors show minimal degradation. Antimatter catalyst reserves remain stable. The exhaustless field drive exhibits consistent microthrust. Warp curvature, though modest, has proven sustainable at low distortion levels. Each system alone was revolutionary. Together, they enabled interstellar transit within a human career span. Dr. Rao reflects during a log entry. We once believed the stars required a single miraculous breakthrough. Instead, they required convergence. Electric propulsion taught efficiency. Nuclear taught density. Antimatter taught precision. Warp taught geometry. Field drives taught subtlety. Magnetic sails taught humility, that sometimes the universe pushes back if we let it. The narrator's voice rises with quiet triumph. This is the maturation of propulsion. Not domination of physics, but partnership. As the binary suns cast intersecting shadows across AURORA's hull, construction of an orbital energy lattice begins. Fusion reactors on Eos surface paired with solar collectors in space, forming a self-sustaining network. Future vessels will depart not with towering fuel stages, but with modular propulsion architectures assembled in orbit, tailored for mission profiles across neighboring star systems. The camera drifts outward, revealing AURORA orbiting Eos, mag sail coils stowed, warp ring faintly luminous, fusion exhaust idle for the first time since departure. In the background, the twin stars blaze, symbols not of distance conquered, but of distance yet to be explored. The narrator closes this chapter with a reflective cadence. Propulsion began as fire beneath a metal cylinder. It has become the art of interacting with the universe at every scale, atomic, electromagnetic, gravitational, quantum. And now, under alien suns, humanity prepares to build engines that will carry not just explorers, but civilizations. Fade to the surface of Eos where the first human footprint presses into unfamiliar soil, a fusion-powered lander gleaming nearby. Above, AURORA waits, not as a vessel of escape, but as the prototype of a new era. Eos rotates slowly beneath AURORA's orbit, oceans glinting copper under twin suns. The airless magenta sky of high orbit is streaked with distant micrometeoroids and faint interstellar dust. Within the ship, fusion systems hum quietly. Antimatter catalysts are idle, and the exhaustless field drive maintains subtle microacceleration. The warp ring glows faintly, a reminder that space itself can be negotiated, shaped, and, eventually, traversed with ingenuity. The narrator speaks, low and reverent. Once, propulsion was a battle against gravity. Now, it is a conversation with the universe itself. Crew members assemble in the observation deck. Holographic overlays track star positions, interstellar trajectories, and the faint gravity wells of distant Kuiper Belt objects beyond Eos. Navigation officers discuss the next phase, the networked interstellar lattice. Using Eos as a hub, the plan is to construct modular beamed energy arrays, magnetic sail corridors, and fusion refueling stations across the system. Each structure, explains engineer Kessler, is both propulsion and infrastructure. They bend local forces to our will. The first demonstration begins. A small cargo probe launches from AURORA, no onboard propellant, relying entirely on a combination of field momentum drive and an external laser beam from the orbital array. Its sail unfurls in the sunlight, an engineered surface of metamaterials reflecting photons with near-perfect efficiency. The probe accelerates gradually, leaving orbit with a smooth, silent surge. Sensors confirm acceleration that would be impossible with conventional propulsion. The narrator observes, "We once thought momentum required mass. Now, it can be borrowed from light itself." Meanwhile, fusion-powered mining units descend to Io's surface to extract helium-3 and deuterium. Processing modules convert raw materials into fuel pellets for interstellar vessels, while power converters supply energy to orbital laser arrays. AURORA functions as command node, ensuring precision coordination across kilometers of orbital and surface infrastructure. A test of combined propulsion modes follows. A small crewed shuttle detaches from a main vessel. Fusion engines engage for primary thrust, antimatter-assisted pulses provide short-duration boosts, and the field momentum system supplies continuous microthrust. As the shuttle approaches the orbital laser array, its sail captures the beam and acceleration climbs significantly. Magnetic navigation coils stabilize orientation without gyroscopic mechanisms. In real time, it achieves velocities previously attainable only by deep space vessels with full propellant loads. The narrator's tone grows visionary. The future of propulsion is orchestration, not a single engine or breakthrough, but the careful alignment of multiple complementary forces, a symphony of atomic, electromagnetic, quantum, and gravitational interactions. Meanwhile, within the ship's lab, quantum vacuum sensors detect subtle anomalies in local space, a residual effect of low-level warp distortions. Engineers hypothesize that by modulating the exhaustless field drive in concert with these distortions, they can slightly enhance velocity without additional energy input. Simulations confirm that cumulative small boosts could compound over decades to approach interstellar fractions of light speed. Elsewhere, a fusion-powered tether extends from orbit to the surface of Eos. Nanostructural arrays carry energy and propellant along the tether using electromagnetic pumps, reducing mass dependency for orbital insertion. The crew watches the process unfold, understanding that in-system propulsion can now become a renewable, networked operation. Spacecraft no longer reliant on finite onboard propellant, but integrated into a living web of energy, momentum, and matter exchange. The narrator reflects. From chemical flames to plasma whispers, fission fire, fusion union, antimatter sparks, warp curvature, field momentum, and now light itself, propulsion has matured into a discipline of interaction. Every engine a dialogue with the universe. Every trajectory a conversation with the laws of physics. As twilight falls over Eos oceans, AURORA begins preparations for departure from the system. Fusion engines fire for a modest push, enough to break orbit while conserving antimatter and field drive reserves. The warp ring stabilizes, maintaining low-amplitude curvature for the next phase of interstellar travel. Magnetic coils monitor and adjust for solar wind interference from the twin stars. The camera pans outward, capturing AURORA as a luminous sentinel against Eos twin sunsets. Drones flit across orbital arrays, reflections of humanity's ingenuity. Probes sail silently toward distant exoplanets, capturing data on atmospheres, radiation belts, and planetary composition. Each measurement informs propulsion strategies for ships, yet to be constructed. Finally, a communications relay signals back to Earth, delayed by decades light years, confirming arrival, operational success, and performance metrics. The first interstellar hub is established. Humanity now possesses a blueprint for expansion. Modular propulsion systems, hybridized engines, and energy networks spanning multiple star systems. The narrator concludes with quiet authority. We have not only crossed the solar system, we have learned how to bend forces, borrow momentum, and harness energy in forms once thought unreachable. Propulsion is no longer simply motion. It is mastery of interaction. And with mastery comes the promise of voyages beyond imagination. fade to distant stars, each a potential waypoint, each requiring the orchestration of every propulsion method ever conceived. AURORA glides forward, luminous against the darkness, a pioneer among the first corridors of human interstellar travel. The void stretches ahead, black and infinite, yet threaded with distant suns. AURORA glides at the confluence of every propulsion breakthrough humanity has achieved. Fusion engines hum steadily. Antimatter catalysts lie dormant but ready. The exhaustless field drive provides subtle, continuous thrust. The warp ring pulses faintly, and magnetic sails stand ready for photon-assisted acceleration. The narrator's voice rises, resonant and final. For a century, propulsion was the art of survival. Today, it is the art of possibility. The ship leaves the EOS system behind, entering interstellar space proper. Data from the twin suns fades slowly, replaced by the sparse glow of distant stars. Even here, in the vastness, propulsion is alive, a symphony of technologies interacting seamlessly. Fusion maintains baseline acceleration. Antimatter microbursts add precision. Exhaustless microthrust accumulates over months. Warp curvature shortens paths imperceptibly, and distant lasers beam momentum through deployed sails. The ship moves as though it were part of the universe itself, not merely moving through it. Crew members gather in the observation deck, staring at the velvet black dotted with pinpoints of light. "We have crossed more than distance," AURORA whispers. "We have crossed boundaries of thought." A holographic display shows mapped trajectories to the nearest star systems. Alpha Centauri, Proxima Centauri, Barnard Star, Wolf 359, each reachable in centuries, decades, or with continued refinement of warp and field momentum technologies, in years. The narrator continues. Every engine was a lesson. Every experiment a proof that limits are not fixed. They are negotiable, adaptable, subject to understanding and ingenuity. AURORA begins long-duration burns, combining propulsion modes. Tiny accelerations, imperceptible to the human body, compound across thousands of kilometers. Sensors measure minute curvature in space-time, residual warp oscillations stabilized by automated control loops. The field momentum drive hums silently, its cumulative effect now visible in precise navigation readings. Suddenly, sensors detect a faint gravitational lens, an unseen mass drifting between the stars. The crew maneuvers using antimatter-assisted pulses and fusion guidance, adjusting trajectory with finesse. No traditional propellant is wasted. Microacceleration and field interactions perform delicate steering. The ship threads past the invisible obstacle with millimeter-level precision, demonstrating that propulsion is now as much about control as it is about speed. The narrator reflects philosophically. Humanity once feared the vacuum. It feared isolation, immensity, and impossibility. Now, we understand that the void is a partner, not an adversary. Its subtle currents, its latent energy, its curvature, all are instruments in the orchestra of motion. In preparation for long-term exploration, the crew deploys autonomous probes equipped with miniaturized hybrid propulsion, scaled, fusion engines, micro-antimatter catalysts, and compact field momentum systems. They sail outward ahead of the ship, mapping interstellar magnetic fields, particle streams, and radiation hazards. Data streams back, informing navigation and refining models for the next generations of interstellar craft. Fusion reactors provide continuous power to sustain life support, laboratory experiments, and propulsion support systems. Antimatter reserves, carefully monitored, serve as emergency thrust for critical maneuvers. The warp ring remains in low-amplitude mode, providing a small but meaningful reduction in effective distance to future stars. The exhaustless drive hums quietly, compounding velocity incrementally, a silent force magnifying centuries of foresight. AURORA reaches the outer boundary of the local interstellar cloud. Gas densities drop, cosmic rays intensify, and magnetic fields become more variable. Navigation and shielding systems respond in real time, using layered propulsion to maintain course. The ship glides with elegant efficiency, a testament to human ingenuity, not brute power. AURORA logs a final message, speaking into the ship's historical record. We are no longer confined by the mechanics of yesterday. Each engine, each system, each experiment has taught us that distance is not a wall. Space is a medium, energy is currency, and motion is negotiation. What we leave behind is not only data or maps. It is the blueprint for civilizations among the stars. The narrator concludes, voice full of awe. From fire to plasma, from fission to fusion, from antimatter sparks to the bending of space-time and the harnessing of momentum itself, propulsion has evolved beyond the mechanical. It is no longer about engines. It is about understanding the universe and moving within it with grace, precision, and imagination. The horizon is unbound, and humanity moves forward